Hello and welcome to this lesson on refraction, which is part of the waves topic in AQA A-Level Physics. So in today's lesson we're going to look at investigating the phenomena of refraction. So if we've been successful and we've learned in today's lesson, we should be able to state Snell's law. We should be able to explain what happens to the speed of light waves when they enter materials such as water, and we can finally relate refractive index to the speed of light waves. So in today's lesson we're going to be looking at the following part of the AQA A-Level Physics specification, 3.3.2.3 refraction at a plane surface. So when a wave meets a boundary between two materials, in general some of its energy is reflected and the remainder is transmitted into the new material, as shown below in this particular diagram. Now the principle of conservation of energy means that at the boundary between two materials, the energy of the reflected wave added to the energy of the transmitted wave will be equal to the total energy of the incident wave. Now the wave speed depends on some of the properties of the medium. So what this means is as a wave crosses a boundary between two mediums, it will speed up or slow down. So for example, light waves travel at a higher speed in air than light does in water or glass. So therefore, you also see that water waves will slow down when they move from deep to shallow water. So refraction is the change in the direction of a wave that occurs due to the change in wave speed as the wave travels from one medium to another. Now lots of different waves refract. So for example, sound waves can refract. So sound waves travel faster in warmer air than they do in colder air. So at night a temperature inversion may occur where the air near the ground is warmer than the air higher up because of human activity. So therefore sound waves will travel faster in the warmer air, so therefore will refract and curve back downwards towards the ground at night, which is why you can often hear things at night from a distance compared to what you can during the day. Now it's also important to note that when a wave slows down, the wavefronts of the wave get closer, as shown in this particular diagram. So this is to be expected because we know wave speed is equal to frequency times y wavelength, or c equals f lambda, and the frequency is determined by the source of the wave emitter and it remains constant throughout the process. So what you can see is because this takes place, that if the speed decreases, well then the wavelength must also decrease. Now, as well as that, I mean, the intensity and the amplitude of the wave also decrease slightly upon refraction because a small portion of the wave also reflects, but this isn't as noticeable as the change in speed and wavelength when the wave changes medium. So a wave will change direction when it enters a new medium, when it hits that medium at an angle. So when the waves strike a boundary at an angle, part of the wavefront reaches the new medium before the rest of the wave. So that part will therefore change speed first, so it will slow down before the rest of the wavefront. So what this means is that as the rest of the wavefront enters the medium and therefore slows down, the wavefront then changes direction. It has been refracted. So when a wave enters a more dense medium, it slows down and deflects towards the normal. Whilst when a wave hits a less dense medium, it will speed up and move away from the normal. Now the change in angle depends on the ratio of wave speed in each medium. Now the bigger the change in wave speed, the bigger the change in angle. Now this leads to a new property, something that we call the absolute refractive index, which is given the symbol n, and that's a property of a material which measures how much light slows down or speeds up when passing through it. Now it is the ratio between the speed of light in a vacuum, c, and the speed of light in the material, cs. So we can say that the absolute refractive index is equal to c over cs, where c is the speed of light in a vacuum, which is 3 times 10 to the 8 meters per second, and cs is the speed of light in that particular substance. So the absolute refractive index of a material is a property of that material only. So light travels at different speeds within different substances depending on their refractive index. So a material with a high refractive index is called optically dense, such material causes the light to travel slower. So let's look at an example question of this. The refractive index of plastic is 1.47. What is the speed of light in plastic? So you say N equals C over CS, so therefore CS is equal to C over N. We know C is always 3 times 10 to the 8. N in this example is 1.47, so the speed of light in the plastic is 2.04 times 10 to the 8 meters per second. Now here are some examples of some refractive indices of materials. Now you'll notice a few things. Firstly, the slower the speed of light in the material, the higher its refractive index. Now, since the speed of light in a substance will always be less than the speed of light in a vacuum, because the speed of light in a vacuum is the fastest speed in the universe, the value of n is always greater than 1. Now, materials with a high refractive index are referred to as optically dense. So in this example, diamond is the most optically dense material. Now, in calculations, we can say that the refractive index of air can be taken as approximately 1. It's 1.003. Now, this indicates to us that light doesn't slow down significantly when traveling through air as opposed to traveling through a vacuum. However, just be aware that this value does depend on the density of air, which does vary with its temperature. Now, it's always important that when you're doing your calculations to always double check that the refractive index you calculate is greater than 1. Now, when light is refracted at the boundary between two materials, the amount of refraction depends on the ratio of the refractive indices of the two materials. So as you can see in the following diagram, we've got an example of where a light wave is transferred between two materials. Now, we call theta 1 in this example the angle of incidence and theta 2 the angle of refraction. Now, something called Snell's law links the angle of incidence and the angle of refraction with the speed of light in each medium. Now, from observation, you'll know that light will move towards the normal if it passes through from a less optically dense material into a more optically dense material. Whilst we also know that it will move away from the normal if it passes from a more optically dense material into a less optically dense material. So all we can do with this is take this information and we can work out what Snell's law of refraction is. So Snell's law of refraction for a boundary between two materials is given by the equation n1 sine theta 1 equals n2 sine theta 2, where n1 is the refractive index of the first material, n2 is the refractive index of the second material. Theta 1 is the angle of incidence of the ray in the first material, and theta 2 is the angle of refraction of the ray in the second material. Please do remember that the angles are always taken from the normal, and material 1 is the one the ray goes through first, and material 2 is the material the ray goes through second. Now, we can also work out a value which is n1 n2, which is n2 over n1, which is known as the relative refractive index. Now, the relative refractive index has no units, it's a ratio. So it's also a ratio of the speed of light in material 1 compared to the speed of light in material 2. So we can say it also equals the speed of light in material 1 divided by the speed of light in material 2. So we can combine our two equations here is shown to say that C1 over C2 equals N2 over N1, and we can use this equivalence to work out values if needed. So if you're given 3, you can work out the fourth value. Now, the relative refractive index is a property of the interface between the two materials, and it's different for every possible pair of materials. Now, it's interesting to note that if two materials have the same refractive indices, well, then the relative refractive index between the two of them will be 1. So therefore our refraction will be perfect, so it would fully deflect the wave without distortion. So in theory it would make the object invisible. So an invisibility cloak could work if the refractive index was always identical to that of its surroundings. Now, back to Snell's law. We know that, like we said, n1 sine theta 1 equals n2 sine theta 2. Now again, for this to be true, the incident ray, refracted ray and the normal must all lie in the same plane. And this law is based on Fermat's principle, which states that light will take the path that minimizes its journey in the material. Now, when you're doing calculations with Snell's law, it's always important to check that the angle of incidence and the angle of refraction are the angles between the normal and the light ray, and if the angle between the light ray and boundary is calculated, instead you calculate your angle by doing 90 minus theta, because when you're normal it's always perpendicular to the boundary, so you can get the correct angle. So let's have a look at an example question for this. Calculate the refractive index of material 2 in the diagram given that material 1 has a refractive index of 1.2. So we know that n1 sine theta 1 equals n2 sine theta 2. So n2 is therefore equal to n1 sine theta 1 over sine theta 2. So we pop our numbers in and we say that n2 is going to be equal to 1.2 sine 39.5 divided by sine 27.5. So n2 equals 1.65. Now that makes sense because you'll notice this material 2 must be more optically dense because the angle of refraction is smaller than the angle of incidence, so the wave must be slowing down, so it's in a more optically dense material. So to summarise what we've looked at in today's lesson, we've looked at the idea that the refractive index of a substance is n equals c over cs. You should recall that the refractive index of air is approximately 1, and that Snell's law of refraction for a boundary is n1 sine theta 1 equals n2 sine theta 2. So if we've learned in today's lesson, we should be able to state Snell's law, explain what happens to the speed of light waves when they enter materials such as water, and finally relate the refractive index to the speed of light waves. So thank you very much for watching this lesson on refraction, which is part of the AQA A-Level Physics topic of waves. Thank you very much and have a lovely day.